Hello and welcome to the sixth session of the manufacturing science, machining science course discussion. Now, let me remind you that what we said in our earlier class is that if we have a tool given in one of the systems, okay, either in ASA or in ORS or in NRS, okay, we have to convert that system of the tool angles in another system if we are using that tool there, all right, meaning that ASA system cannot be directly used in the ORS system if you do not convert those angles, because that is required for the regrinding of the tool. That is one thing. So, then we said that the conversion from one system to another system is not so difficult, and we have shown this. If you look at this system, for example, here what we have shown here is the base plane, and then we have made here all the views and the sectional views of ASA system and the ORS system, and then they are correlated through simple geometry which has been shown in here. All right. So, if you look at it, you will see that easily you can actually convert from the ORS system, for example, so from the ORS system to the ASA system, and from ORS system to the ASA system in this way. All right. So, here it is the tool inclination angle, and here is the orthogonal rake angle. Similarly, what we said is that the ORS system also can be converted to NRS system by projecting the axis from the ORS system to NRS system. In here it is shown that the Z0, this is the system of axis Z0 X0, this has been projected to the normal rake system when it is inclined with an angle of I with respect to the Z0 axis or the orthogonal rake system axis. Then if the tool is projected in the Zn and the Xn axis, okay, this is the Xn axis will be perpendicular to that. In that case, it can actually be said to be the tool which is this B0 Qn, and this is the tool as in case of the normal rake system. So, therefore, this angle between the rake face, newly formed rake face which is in the normal rake system, and the X0, this can be considered as the normal rake system. So, we have converted the alpha 0 to alpha n, that is orthogonal rake to normal rake system, and again through the geometry as it is shown here, you can easily convert the normal rake system to the the ORS system. All right. I hope this is clear from here. Next, what we will be discussing in this session is the selection of tool angles, meaning that how we can select the tool angles out of all those angles. Let us say take any of these systems, let us say ORS system. Okay. In ORS system we have the rake angle. How to select the rake angle for a certain set of materials, tool materials and the workpiece materials, and certain set of tool parameters. Okay. These are the factors which depend or which dictate us how to select the rake angles, for example. With 0 inclination angle or the back rake angle, the chip will be flowing parallel to the work surface and may cause removal problem. If we do not have any inclination angle or the back rake angle, the chip will not be it will not be possible to remove the chip, because it will flow parallel to the workpiece surface and it can actually entangle with the workpiece. Okay. With appropriate inclination angle, therefore, or the back rake angle, the chip can be made to flow away from the workpiece, okay, and it can then go along the flow along the rake face of the tool, and on the rake face you can have some chip breaker, okay, and the chip while flowing will hit the chip breakers and the chips will be broken. So, the chip removal problem will be solved if we have certain values of the inclination angle or the back rake angle. If they are 0, in that case the chips will be flowing parallel to the workpiece surface and it will not be possible to remove the chips. That is a big problem in the machining to dispose of the chips, okay, but because otherwise it will entangle with the tool and the workpiece, it will scratch the already machined workpiece surface and it will spoil the surface finish of the workpiece. Similarly, side rake, orthogonal rake and the normal rake, these are the three rake angles in three different systems. This is in ASA, this is in ORS and this is in the NRS system. These angles influence the cutting forces, power and the surface finish. Okay. These are very important angles, whereas the back rake angle, for example, it will not affect the surface finish or the power and the force, cutting force. The larger is the rake angle, the lower are the cutting forces and power and better is the surface. This is the in general. Now, what we mean to say is that if the side rake or orthogonal rake or the normal rake system, if it is large in value, in that case the force will be decreasing. I will give you the reason or the physics behind it. Let us say what we said is this, that if we have in this, okay, in this let us say we have in this axis it is the force, let us say cutting force, in this axis we will have a alpha. This alpha by alpha we mean to say either it is an orthogonal rake or it is a normal rake, okay, as it is given here, as you can see that, or it is a side rake, orthogonal rake or the normal rake. Okay. Yeah, it can be also side rake angle. So, in case when this is more, so the force is going like this, meaning that for the less value of these angles the force will be higher and for higher values of these angles force will be less. Now, why it is so? What is the physics behind it? Let us take an example of the turning. Okay. Let us say here we are having the process, this is the workpiece, okay. This is the tool, this is the tool with certain rake angle, all right. Let us say here the rake angle is alpha 1, okay. This is alpha 1. So, as you know that this is the shear plane, all right, and this is the depth of cut, or in orthogonal cutting also it is the T1, which is uncut thickness. We will discuss these things little later. Now, for this we now increase the value of the alpha, okay. This one of these alpha, of course, the side rake angle, orthogonal rake angle or the normal rake angle. So, let us say we will increase it, we will increase means we will make it like this, okay. So, this alpha is now increased to alpha 2, alpha 1 is increased to alpha 2. Then what happens with the flow is the chip will be like this and the shear plane will be something like this. If the shear plane was here for the alpha 1, for alpha 2 the shear plane will be like that. So, this is the angle between the shear plane and the cutting velocity vector, which is called the shear plane angle. This is let us say phi 1 and this is phi 2. Okay. So, what is happening overall, that the shear plane is decreasing in length, all right. Therefore, less amount will be machined and the force and the power consumption will be less and the surface finish will be better, because the force requirement or the force applied to the process will be less. Okay. So, less force Fc cutting force, the power we will discuss in details later on also. The power is given by the Fc and the Vc. So, if the Fc is less, so the power will be less, all right, and the finish will be better. So, therefore, the finish is better. So, this is what happens when the alpha increases. As alpha increases, force will be less, power will be less and the finish will be better. And this is the physics behind it, that as the alpha is increasing, then the shear plane is decreasing and the less amount will be, less force will be required to remove that material with the less shear plane length, okay, and the force requirement will be less as well as the power will be less. Power is given by the product of Fc and the cutting velocity vector, which is the Vc. For the large rake angles, however, meaning what we are saying is that if we are increasing the rake angle, that means less power, that means it is better. So, let us increase the rake angle. But what happens is that, as you can see, suppose I will draw it again because it is very cumbersome here. Let us say this is a tool which has a rake angle of alpha 1, okay, and we are increasing that rake angle and making that rake angle as alpha 2. So, as a result, what is happening is its tool is becoming thinner. Okay. Tool is becoming thinner means the tool strength is going down, all right. So, as alpha is increasing, so tool becomes thinner. Okay. Thinner means less stronger, right, that is less stronger, less strong. So, that is one reason, and another reason is that as the tool rake angle is increasing, the material available here will be less, and the material available less means that less material is available for heat conduction. Okay. So, the less material available for conduction of heat. So, this is important because otherwise the heat will be accumulated in the tool, okay. And during the process, as we have seen that as the cutting process increases and as the cutting velocity increases, the temperature increases, and the temperature, once again I will repeat that this is root over Vc. So, as the temperature is increasing, that means this is to be conducted, this has to be taken away. Of course, majority of the heat is taken away by the chip, all right, but still the chip is in constant touch with the tool. So, therefore, that some of the heat will be conducted to the tool, and if that heat is not taken away, okay, then the tool will have the thermal deformation and the geometry will be lost. So, therefore, this is important that there should be more material available for heat conduction. So, therefore, we cannot infinitely increase the rake angle of the tool, because if we increase the rake angle of the tool, of course, we will get the benefit of having the less power and the less force, but we are having the less material available for heat conduction, then the tool will be thermally deformed and there will be less strength of the tool, because tool is getting thinner, as we have I have shown it here. All right. So, these are the things which are described here, that large rake angles, however, decreases cutting angle between the rake and the principal flank. So, what we mean to say is that cutting angle is this angle. So, if the rake angle is, this is the cutting angle, and if the rake angle is increasing, then this cutting angle is decreasing. Okay. Let us say this cutting angle initially was for alpha 1, and this is the cutting angle which is less for the more value of the alpha, that is the alpha 2, and less metal is available to support the tool. As I said, to support the tool means to make the tool stronger, okay, and the less metal is available, so that the tool in that case become thinner and strength becomes less, that is the less strength of the tool, and conduct the heat generated due to plastic deformation and the friction. So, the heat generated in the machining process overall, this will be basically, as we said earlier, this is mostly because of the plastic deformation which happens in the shear zone or the shear plane, okay, and because of the friction between the chip and the rake face, but mostly it is because of the plastic deformation. So, this heat generated due to plastic deformation and friction has to be conducted, and less material, if the less material is available, that is when you are increasing the rake angle, in that case the tool will be thermally deformed, because more heat will be accumulated in the tool. Next point is that rake angles may be positive, negative or negative depending upon the desired tool strength. For rough machining, often carbide tools with negative rakes are used. If we remember, we have discussed that the tool may have a shape, okay, which is let us say all right, where we have the 0 rake angle, or we can have a negative rake angle. This we have discussed, all right, and this is the negative rake angle. In the case of negative rake angle, as you can see, the tool is fatter. Okay. That means, tool strength will be more and more material will be available here for the heat conduction. So, therefore, whenever you have a high speed machining, for example, there the temperature produced will be more, the require and the force will be more. So, therefore, the tool strength has to be higher. So, in that case, the such tools as with the negative rake angle, they are normally used, that is what it is said. Rake angles may be positive or negative depending upon the desired tool strength, meaning that if we have to have the tool strength higher, we have to have the negative rake angle. For rough machining, often carbide tools with negative rakes are used, because in the rough machining more heat will be produced. So, we need to have more material for the heat conduction, and we have to have the higher strength of the tool, because the forces will be higher. To withstand the higher forces, the strength of the tool has to be higher. Side rake angle, orthogonal rake angle and the normal rake angle usually vary between 5 to 15 degrees for single point high speed steel tool, depending upon the work material. See, the 5 to 15 is a wide range, of course, it can be 5, 6, 7, which one of that out of that. Now, here it is said that if we have, for example, a high speed machining, or you need to have rough machining, in that case you have to have the less value of the rake angles, because the less value of the rake angles will give you the fatter tool and the more material available for the heat conduction. So, this is how judicially you have to find out that which exactly value that you will be taking, depending on what is available, what is the combination of the workpiece and the tool, what is the material of the tool, and so on. Okay. Higher values are used for softer work material like aluminum, because higher values in softer material force will be less, okay, power consumption will be less, all right, and therefore, you do not need to have the high strength of the tool. So, therefore, large values can be used. In general, harder is the work material, lower is the rake angle. I have already explained it to you. Why? Because you need to have more strength for the hard work material. So, for steel, for example, the recommendations are that these rake angles, that is the side rake angle, orthogonal rake angle and the normal rake angle, they are from 8 to 12 degrees normally. Okay. So, again selection of between 8 to 12, it depends on whether the work material is harder or whether the machining is at high speed, all right. So, you understand that, and if the softer material available, workpiece material is soft, in that case you can have the larger values of these in the range of 10, 12 and so on. For cast iron, this is hard material, supposed to be brittle and the hard material. So, the alpha is between 5 to 10 degrees. This is the normal recommendation, but again you have to judicially find out that what exactly you will be using, which value you will be exactly using, again depending on the condition of the machining and depending on the combination of the tool and the workpiece material. Okay. Let us see about the flank angles. Now, as we said, the flank angle is between the flank face and the already machined workpiece. Now, as you understand that the flank angle is required to save the flank face from being rubbed over the machined surface, so that it does not rub against the machined surface to spoil it further. So, therefore, as much as possible you go with the flank angle, okay, as much as possible you can have it, because the particularly flank angle does not have much effect on the cutting force or the power consumption, that is one thing. Now, again if you are increasing the flank angle, the cutting angle that I have shown it to you earlier, this will be less. With a particular rake angle, if you are increasing the flank angle, the cutting angle between the two faces, the rake face and the flank face, this is decreasing. Cutting angle decreasing means the less material again will be available for the heat conduction and the tool strength will be less. So, therefore, although increasing the flank angle will help you in avoiding the rubbing between the flank face and the already machined surface, but it will again lessen the strength of the cutting tool and less material will be available for heat conduction, because the cutting angle will be less. Okay. So, therefore, there is an optimum way of finding out, or the optimum value can be found out, so that the machining can be optimally performed. These are the things which are described here. Flank angle minimizes rubbing of flank faces with the machined surface, as I explained it to you. Higher values of flank angle will reduce the rubbing, but also weaken the tool. Flank angles have no influence or almost no influence on cutting forces and power. So, angles large enough to avoid rubbing is generally chosen. Now, the angle, that is the normal recommendation, is the 5 to 12, between 5 and 12 degrees for high speed steel, and within that higher values for the softer workpiece material and lower values for the brittle workpiece material. You understand that those reasons we have already told in case of the rake angles. So, this is the same, that the tool is getting thinner, tool material is less available for the heat conduction. This remains the same argument in the case of the flank angles also. Now, the cutting edge angles. I will remind you that the cutting edge angles are those angles which are made between the cutting edges. So, this is the principal cutting edge, this is the auxiliary cutting edge, and the cutting edge angles are this is the principal cutting edge and the auxiliary cutting edge. Okay. Now, these edges or these angles are given to clear the cutting edge from the machined surface. Here we have the machined surface where the flank angle is, flank face is rubbing against the machined surface. So, these edges, okay, have to be cleared so that they are not rubbing against the machined surface again. This reduce the tool chatter, to reduce the tool chatter. Otherwise what will happen, that if one of these angles is more, then the forces which are actually taking out the tool from the workpiece, radial forces, I will explain those radial forces just after this. So, these components will be higher, okay, and the tool will start chattering. Chattering is the self excited vibration. Okay. So, to reduce the chatter, which is the self excited vibration, we have to control the cutting edge angles. Affects the tool life as well as the surface finish. Reason is the same as given for the flank angles and the rake angles. All right. Now, the nose radius. If we have a very sharp tool, okay, as you understand that immediately during the cutting process, this will actually come in contact with the workpiece. So, this will be either rounded off or it can be broken. Okay. It can be broken because sharp tool will always have a very high stress concentration, that is one thing. Let us say this is that sharp tool. So, around this the stress concentration will be very high. So, because of that, as the tool is getting in contact with the workpiece, this will be crumbled or it will be it can be broken. So, therefore, normally the tool nose radius is given, all right, certain nose radius is given, so that this does not happen, and this is recommended to be from between 1 and 3 millimeter. Okay. So, if it is less than that, then the stress concentration will be higher and the tool wear will be high, tool may be broken, tool may be crumbled, it may be thermally deformed and so on. It is if this value of R is higher than 3 millimeter, in that case again that phenomena will come, that is the chatter formation, meaning the self excited vibration, that is those components which will start detracting the tool from the workpiece, okay, then again cutting force will take it back and again it will be detracted. So, this is the chatter, this is the self excited vibration which will happen if the radius, tool nose radius is more than 3 millimeter. So, this nose radius improves the tool life and the surface finish. You understand that? That surface finish will be improved because if it is very sharp tool or let us say less value of the tool nose radius, then the feed marks will be remaining on the workpiece. And we will discuss in a chapter called surface finish, then I will explain it to you that how the surface finish varies if the tool is sharp and in case the tool has a nose radius. Then it will be clear to you that why the surface finish is improved if a tool nose radius is given. So, basically it is because when the tool is sharp, these feed marks will be there, more prominent feed marks will be there, and if the tool nose radius is given, the feed marks, they will be overlapping on each other, and overall the surface roughness will be less. So, the tool the surface finish will be better. Large nose radius increases cutting forces and power. Okay, I explained it to you because it will be rubbing and also it will have the chatter, self excited vibration. So, the recommended values are between 1 and 3 millimeter, as I said. So, these are the factors, that means the 3 sets of angles. Once again, this is the rake angle, flank angle and the cutting edge angles. These 3 sets of angles are very important for to regulate and judiciously selecting their values, so that the surface finish could be better, so that the less power can be consumed. I mean, in the process the less force is applied. So, overall our output should be, or our aim, final aim has to be that once again during the machining, our aim is to get the final product with the right shape, size, finish and accuracy. So, this shape, size, finish and accuracy, they will broadly depend on the right selection of these parameters, that is the particularly the rake angle, of course, the flank angle and the cutting edge angles and the tool nose radius, all right. And all these factors that we have explained, that are the reasonings why these things happen. So, I will once again remind you or repeat that here the rake angles are more important, that is the side rake, orthogonal rake and the normal rake, because on these angles the power consumption and the force will depend. And as I explained it to you, that force will be reduced as the rake angle is increased. Okay. But we cannot increase the rake angle infinitely, because as the rake angle is increasing, then the tool is becoming weaker and the less material is available for the heat conduction from the tool. So, then the thermal deformation of the tool will happen and it will be not withstanding the high force. That means, if the tool is thin or weak, in that case the with the high cutting force, the tool will be deformed again or tool can be broken. So, therefore, there has to be a value which is in between, it cannot be very high, it cannot be very less. For example, if it is very less, in that case that force will be very high. So, again the tool will be affected. So, these are the factors which have to be taken into consideration while selecting the values of the angles, rake angles, flank angles, cutting edge angles. Of course, flank angles, it is not much of a problem as in rake angle, because flank angles do not have much effect on the cutting forces and power, but it will again rub the workpiece, okay, the machine surface. So, give as much as possible. Again, you cannot increase infinitely because the tool angle, cutting angle is less. So, therefore, you have to judicially again find out what is the angle suitable for that particular operation. The rest of the things I will discuss in the next class. Thank you.